Okay, we're trying to finish up section 7.1. We did example 4. Now we want to talk about converting from rectangular to polar and vice versa. So, convert rectangular equations now to polar equations and vice versa. So we want to make sure that we can convert rectangular equations to polar equations and vice versa. 1 second. Okay, convert polar equations to rectangular equations to polar equations and vice versa. So we had a few equations that would help us. X was r cosine theta, y is r sine theta, tangent of theta is y over x, and x squared plus y squared equals r squared. Those were the three things, or the four things, I'm sorry, that would help us convert either from polar to rectangular or from rectangular to polar. So with this in mind, let's do example, I'm going to go ahead and skip to example 6. Example 6 says write an equivalent equation using polar. So write an equivalent polar equation. Okay? Write an equivalent polar equation. All right. Well, the one they give us, A, says 2x plus y equals 4. So again, I'm using these things. X is r cosine theta, y is r sine theta, tangent of theta is y over x, and x squared plus y squared equals r squared. So when I see x, I can replace that with r cosine theta. When I see y, I can replace that with r sine theta. That's equal to 4. Okay? Well, there's an r in both of these terms. I can factor it out. That, and I'm going to solve for r. And you can think of this, you can think of solving for r kind of like when we had rectangular equations. A lot of times we'd solve the equation for y. We'd have y equals 2x plus 1 or y equals negative 3x plus 5. So we can kind of think about solving the equation for r kind of in the same vein of when I was in rectangle, I solved some of these equations for y. So there's A. Let's do B. B says x squared plus y minus 2 squared equals 4. X squared y minus 2 squared equals 4. Okay. X squared plus y minus 2 squared equals 4. Make sure that's all on camera. Okay. So again, everywhere I see x, I'm going to replace it with r cosine theta. But I got a squared. Y is r sine theta. Minus 2, that's squared. That's equal to 4. Okay? And so now I'm going to square everything. R cosine theta squared will give me r squared cosine squared theta. This I got to be careful with because really this is a for method because r sine theta minus 2 squared means r sine theta minus 2 times r sine theta minus 2. Okay? And I'm going to have to FOIL that out. Okay? I'm going to have to FOIL that out. So I got to be a little bit careful. I don't just get r squared sine squared minus 4. This thing squared means that thing times itself. So I'll still have the r squared cosine squared theta. For this out, r sine theta times r sine theta is r squared sine squared theta. The outer product would be minus 2 r sine theta. The inner product would be minus 2 r sine theta. So the outer and the inner combine to give me minus 4 r sine theta. And then negative 2 times negative 2 gives me plus 4. And that's still equal to 4. So again, the outer product was negative 2r sine theta. The inner product was negative 2r sine theta. Those two combine to give me negative 4r sine theta. Okay, so if I look at these first two terms right here, cosine squared, I can factor out the r squared minus 4r sine theta. And if you subtract 4 on each side, okay, if you subtract 4 on each side, you'll just get equals 0. Okay? If we subtract 4 on both sides, it equals 0. Well, cosine squared theta plus sine squared theta is 1. So I get r squared minus 4r sine theta equals 0. Again, cosine squared theta plus sine squared theta equals 1. That's one of those Pythagorean identities. Okay? I can factor an r out. And I get that. Okay? If I factor the r out, I get that. And so I've got a product equal to 0. So either this one equals 0 or this one equals 0. Adding sine theta means that this one equals 4 sine theta. So I get two solutions, either r equals 0 or r equals 4 sine theta. And what I want to notice is, if theta, what I'm going to basically show is that this solution right here, r equals 4 sine theta, really contains this one. So I really won't have to worry about him. Because think about if theta were pi. If theta were pi, the sine of pi is 0. So 4 times 0 would be 0. So r equals 0, that solution is already included in him. So this would be the equivalent polar equation. I don't have to write that and r equals 0 because again, r equals 0 is contained in this solution. So I don't have to write him separately. He's already a part of him. Because whenever theta is a multiple of 0, 2 pi, so if theta were 2 pi, sine of 2 pi is 0. If theta were 3 pi, theta with 3 pi, sine of 3 pi is 0. So you'll get r equals 0 for multiple values of theta. So this will be the only one I need. So this equation in rectangular is equivalent to r equals 4 sine theta in polar. Okay? All right, let's do another example. And again, we see again that we solve the equation for r. When you're putting an equation in polar, typically we'll solve for the variable r. Let's do example 7. Example 7 says convert into rectangular form. Convert the equation into rectangular. Okay, so A, they say r equals 2. A says r equals 2. That's obviously an equation that's in polar form, r equals 2. All right, well again, I had those 4 relationships I wrote on the board. If r equals 2, square both sides, and you'll get that r squared is 4. Okay, if r equals 2, then if I square both sides, r squared is r squared, 2 squared gives me 4. But remember, x squared plus y squared equals r squared. So I can replace r squared with x squared plus y squared. And that will give me my corresponding rectangular form. Okay, there's my rectangular form. B. B says theta equals pi over 3. Theta equals pi over 3. Well, I had that other relationship that said the tangent of theta is y over x. Well, they gave me theta, so I can replace theta with pi over 3. So the tangent pi over 3 is y over x. Okay? Well, I know what that is. I can look at my unit circle and figure out what the tangent of pi over 3 is, right? If I look at pi over 3, I'm right here at 60 degrees, or pi over 3 radians. And the x-coordinate is 1/2, the y-coordinate is square root of 3 over 2, right? And so the tangent of pi over 3 would be the y-coordinate over the x-coordinate. That's square root of 3 over 2 times 2 over 1. That's square root of 3. So the tangent of pi over 3 turns out to be square root of 3. Just this, so you can see it. Okay. All right. So again, pi over 3 radians has coordinates. X coordinate is 1/2. The y coordinate is square root of 3 over 2. Tangent of pi over 3 would be the y coordinate over the x coordinate. That means square root of 3 over 2 times 2 over 1, because you keep, change, flip. Keep the 1 in the top, change division to multiplication, flip the 1 in the bottom. The 2's cancel out, and you get square root of 3. So tangent of pi over 3 is square root of 3. So I can replace tangent of pi over 3 with square root of 3, multiply both sides by x, and I'm going to turn it around. And there's your equivalent rectangular form. Okay, y equals square root of 3 times x. Let's look at C. C says r equals 4 cosecant of theta. R equals 4 cosecant of theta. Well, 4 cosecant of theta really is 4 times, or 4 over sine theta, because cosecant of theta is 1 over sine theta. Okay? So I've got r equals 4 over sine theta. Multiply both sides by sine theta. So let's multiply r by sine theta on this side, and I'll multiply by sine theta on this side. Whatever I do to one side, I got to do to the other. These cancel. I get r sine theta equals 4, but r sine theta is exactly y. So there's my corresponding rectangular form. Y equals 4. Okay? All right. So this is a pretty simple process to change from polar to rectangular. This one is a little more interesting, D. D says r equals -8. R equals -8. And we have cosine of theta. R equals -8, cosine of theta. I want to convert that equation. It's in polar form right now. I want to convert it to rectangular form. Well, we've seen already a bunch of times. If I ever get r sine theta, I have y. If I ever get r cosine theta, I've got x. Well, I've got cosine theta, but I don't have the r. So to get an r on this side, I'm going to multiply both sides by r. So if I multiply this r by r, I get r squared. If I multiply by r on this side, I get -8r cosine theta. Because again, I need r cosine theta. I can replace that with x. Well, r squared, the other thing that helped me out is r squared is the same thing as x squared plus y squared. And r cosine theta is x. So at this point, we've got a rectangular equation, but we're going to clean it up a little bit. But at this point, you've replaced all the r's and thetas with x's and y's. You now have a rectangular equation. Well, let's add 8x to both sides. And I'm going to leave a little space here. Plus y squared equals 0. What I'm going to do is I'm going to complete the square. I'm going to complete the square on these x terms. Okay? So to complete the square, I look at the coefficient of x to the first power. I have a +8. Half of +8 is 4. You take half of the coefficient of x to the first power. Half of 8 is 4, but I got to square it. 4 squared will give me 16. Now this thing will be a perfect square. But if I added 16 on this side of the equal sign, Over here, I've got to add 16 too, because I got to keep the equation balanced. The left side was equal to the right side. So if I do something on the left side, I've got to do the exact same thing on the right side to keep it balanced. So I've completed the square at this point. X squared plus 8, x plus 16 is something square. And the beauty of completing the square is the factoring comes for free. Whenever you complete the square, the factoring comes for free. What do I mean? Well, you know you're going to have something plus some or something minus something squared. This thing, when you complete the square, you're going to create a perfect square trinomial. It'll be some binomial factor squared. Well, what goes here? There's got to be an x there, but what goes here? Well, half of a positive 8 is a positive 4. It factors like that every time. You don't really have to factor. Now, if you wanted to, you could figure out the factor. You could say, okay, x times x gives me x squared. 16 is a 4 times a 4. Both of these are positive, so both of these are positive. X plus 4 times x plus 4 is x plus 4 squared. You can figure it out if you want to, but the factoring comes for free whenever you complete the square. Because again, it's going to always be a perfect square trinomial. I had to have the x. Half of a positive 8 is a positive 4. If this had been a negative 8, half of a negative 8 is a negative 4. That's how it would factor. But since it was positive, that's positive. Well, at this point, we're done because we have the equation in rectangular. So there's my corresponding rectangular equation. All right, so that's 7.1. We're done with 7.1. We're in 7.2 now. We have completed everything for 7.1. We are in 7.2 now. So 7.2 is polar equations. Polar equations. Or I'm sorry, graphs of polar equations. Graphs. So graphs of polar equations. We've already talked about polar equations to some degree, but now we're going to talk about how do we graph them? How do we graph these polar equations? Okay? Well, we're going to start out pretty simple. Example 1, graph. They give us r equals 6 sine theta. R equals 6 sine theta. They want us to graph this polar equation. Okay, r equals 6 sine theta. Well, one thing that we can always do, just like in rectangular equations, whenever I wanted to graph a rectangular equation, I could create a t-chart and I could choose x equals something. Like if I want to graph 2x plus y equals 7. I can say, okay, is x is 0? Well, put a 0 where the x was. That's 0, so y turns out to be 7. Then I could choose x equals maybe 2 or x equals -1 and figure out the y coordinates from the equation. So I can plot points, right? If I want to graph something in rectangular, I can plot points. Well, you can do the same thing in polar. It's just usually not quite as easy. But I can do r comma theta in polar. And really, it might be easier to do theta comma r. Because you're going to choose the theta, and then you're going to figure out what the r has to be, okay? So, let's just choose some angles. 0, pi over 6, pi over 4, pi over 3. Let's just start with the standards. 0, pi over 6, pi over 4, pi over 3, pi over 2. And I'll do a few more. Yeah, 2 pi over 3. Okay. They say 3 pi over 4, 5 pi over 6. Pi. We're just choosing angles from our unit circle from 0 all the way around to pi. Okay. And yeah, we can see that. So how do I figure out what the corresponding value of r is? Well, plug it in. When theta is 0, r will be 6 sine of 0. Now, I'm doing radians, so make sure your calculator is in radians if you're using your calculator. Otherwise, use your unit circle. The sine of 0 on your unit circle is 0. So you get 0. So 0, 0 is on the graph. Okay? 0, 0 is on the graph. Well, when theta is pi over 6, you'd have r equals 6 sine pi over 6. Go to your unit circle. The y coordinate when you're at theta equals pi over 6 is 1/2. That'll be 3. Power of 6 comma 3. Or no, we're doing r comma theta. Remember, polar points are always r comma theta. And that was one reason I kind of wanted to write the r here and the theta here, but you put the theta in first and get the r, so that's the only reason I listed it like this. But again, all points in polar better be r comma theta. So 0, 0 is on the graph. This one says 3 power of 6 is on the graph, right? And let's check power of 4. So r equals 6 sine power of 4. That's 6 square root of 2 over 2. 2 goes to 6, 3. So this is 3 square root of 2. And if you want, just get decimal equivalent to this, right? Get a decimal equivalent. Square root of 2 is about 1.4. 3 times 1.4 is 4.2. So when r is 4.2, theta is power of 4. There's my polar coordinate. And I can keep doing this. And in fact, I think I do want to turn that around because it's going to be confusing. All polar points are r comma theta. It's going to be kind of weird how I write it, but I'm going to write r comma theta. And we're going to do the same point. So 0, power of 6, power of 4, power of 3, power of 2, 2 pi over 3, 3 pi over 4, 5 pi over 6 pi. So we already did 0, 0. We did power of 6 comma 3. So again, r theta, 0, 0 is one of my points. 3 comma power of 6 is one of my points. R goes first, theta goes second. So I do want to write it like this, but I'm not going to write it the other way. Let's check power of 3 real quick. 6 sine power of 3. 6 times. Sine of power of 3, look at your unit circle. The sine of 60 degrees is square root of 3 over 2. Again, 2 goes into 6 3 times. 3 times square root of 3. Square root of 3 is about 1.7. 1.7. So 3 times 1.7, 5.1 about. Maybe about 5.1. R is 5.1. And I had, that was 3, this was 4.2, this is 5.1. Okay? Power of 2. R equals 6 sine power over 2. 6. Sine of power of 2 is 1. So I get 6. So 6. And you can continue this. I'm not going to do it. It's in your book. At 2 power over 3, R turns out to be 3 square root of 3, which is again about 5.1. At 3 power over 4, it'll be back at 4.2. At 5 power over 6, it'll be back at 3. And at pi, you're back at 0. Okay? All right. Hopefully that makes sense. Okay? Hopefully that makes sense. Let's kind of see what we have so far. And this is polar now. We're graphing in polar. So when I think about these things, this would be pi over 2. This is 0. This would be 3 pi over 2. This would be, no, this would be pi. I'm sorry. This would be 3 pi over 2. And back around to 2 pi, right? Those are my angles, 0 to 2 pi, right? And I'm going from 1 to 6. So circle radius 1, circle radius 2, circle radius 3, circle radius 4, circle radius 5, circle radius 6. So let's just pop the points we have so far. 0, 0 is right here. That's the pole. Power of 6 comma 3. So again, power of 6, power of 4, power of 3. So 3 comma pi over 6, I make an angle of pi over 6 and I go out 3. That's right here. 4.2 pi over 4, I make an angle of pi over 4. I go out 1, 2, 3, 4.2, about right here. 5.1 pi over 3, so I make an angle of pi over 3. Go out 5.1, 1, 2, 3, 4, 5, 5.1 about right here. 6 comma pi over 2 would be right here. Okay. 2 pi over 3. Okay, I'm along this vector, 2 pi over 3, theta equals 2 pi over 3. 5.1, so back here. 4.2, when theta is 3 pi over 4, I'm on this vector. 3 pi over 4, 4.2, so 1, 2, 3, 4.2. 3 comma 5 pi over 6, so 5 pi over 6 is this vector. 1, 2, 3. And 0 pi, back here. So pretend that's a nice, concentric, nice, smooth, even circle. That's a circle so far. Okay, that's a circle. Okay, if you did it on a good piece of graph paper, you would see that it would clearly indicate a perfect circle. A circle centered at right there. Okay, at pi over 2, well, at 3 comma pi over 2. Okay, now we only did from 0 to pi. So let's just make sure. Let's keep going. And I'm going to leave these here for a second, but let's just see how it works. So let's get bigger than pi. So 0 to pi is from here to here. So then I'll go to here. This is 7 pi over 6. This is 5 pi over 4. This is 5 pi, 4 pi over 3. Okay, 3 pi over 2. This would be 5 pi over 3. This would be 7 pi over 4. This would be 11 pi over 6, and then back around to 2 pi. All right, so let's check 7 pi over 6. And let's just check a few of these. R equals 6 sine 7 pi over 6. That's 6 times. Look at your unit circle. The sine of 7 pi over 6, the y coordinate is -1/2. That's -3. So, when theta is 7 pi over 6, this becomes -3. Okay? Let's check the next one. 7 pi over 6, then 5 pi over 4. 6 sine 5 pi over 4. That's 6 times. Look at your unit circle. Sine of 5 pi over 4 is negative square root of 2 over 2. 2 goes to 6, 3. 3 times negative square root of 2 would be -4.2. So I'll get the same number. It's just now negative. Let's check. So this was 5 pi over 4. Now we're checking 4 pi over 3. R equals 6 sine 4 pi over 3. Look at your unit circle. The y coordinate at theta equals 4 pi over 3 is negative square root of 3 over 2. Okay? So the 2 goes into 6, 3. That's 3 times negative square root of 3. That's negative 5.1. And if you check them, it's going to do this. So this next one would be 3 pi over 2. This would be 5 pi over 3. 4.2 would be 7 pi over 4. This would be 11 pi over 6. So let's see where these points live at. And this first one could have been starting at pi, right? Let's do that one real fast. R equals 6 sine of pi. The sine of pi is 0, though. So that's still 0. So, make an angle of pi, 0. That's right here. Let's do the second one. 7 pi over 6. So I'm on this vector right here. But it's -3. So I'm on this vector, but it's -3. So instead of going 1, 2, 3 in a positive direction, I'll go backwards. 1, 2, 3. I'm back right here. So this part right here, R equals -3, theta equals 7 pi over 6, actually repeats and becomes that point that used to be 3 comma pi over, so what I'm saying is -3, 7 pi over 6 turns out to live in the same place as +3 pi over 6. Then I look at negative 4.25 pi over 4. Well, 5 pi over 4 is this vector, right? But instead of going positive 4.2, which would have been here, since it's negative, I'll go backwards. 1, 2, 3, 4.2. I just repeated that point. And then when I get to negative 5.1, 4.3, it's going to repeat that point. When I get to 3 pi over 2, 3 pi over 2 would be this vector. But it's negative 6, so I go backwards. 1, 2, 3, 4, 5, 6. I'm back here. This point right here would become him. This point right here would become him. This point right here becomes him. And back around. So that's all I get. That circle is my whole graph, whether I'm working from 0 to pi or from pi to 2 pi. So these polar equations can do some really, really weird things when you graph them. So it turns out that I could have just graphed from 0 to pi, and I would have had the entire graph, that circle, that's centered at 3 comma pi over 2. Okay? Even when I graph these points between pi and 2 pi, you could call this one 2 pi if you like, and you're going to get 0. These points from pi to 2 pi are exactly overlapping the points we found from 0 to pi. Okay? So there's my polar equation. Now, so plotting these polar points, just sticking them in the equation, getting R, you take theta, stick it in the equation, you get R. That works for, this is backwards. This should be 2 pi on this side and 0 on that side. The 0 should be here. The angle is on the right. The value of R is on the left. So graphing polar equations, you can just plot points. Okay, but sometimes you have to be really careful about the points, and sometimes we see that these things just repeat themselves. Okay, these things can just repeat themselves. All right. But plotting points works to graph any polar equation. You can literally graph any polar equation plotting points. All right. So let's do some more of this plotting point stuff, or this graphing these polar equation stuff. Okay. We're going to use some symmetry. Symmetry helps us a lot in polar coordinates. Symmetry in polar coordinates. We're going to make use of symmetry. Okay? So it turns out there's 3 ways that polar equations can be symmetric. And I'm going to pause here and I'm going to start this video back